Hey guys, welcome. So in this video, I'm going to introduce arithmetic or arithmetic sequences and geometric sequences. Alright, in a different video, I'll introduce arithmetic and geometric series. The difference between sequences and series is sequences is a list of numbers that frequently have a pattern to them, whereas series is the sum of those numbers in the list. So series is a sum, and then sequences is just a list. All right. Like I said, a video on series to come, introducing arithmetic and geometric series, and lots more videos on sequences and series, both arithmetic and geometric. But yeah, let's look at here an arithmetic sequence to start, or two rather. So here are two arithmetic sequences. The first is 1, 2, 3 all the way to n, and then the second is 3, 7, 11, 15 all the way to n, right? All right, cool. Now, looking at these two sequences, you should get an idea for what we mean by an arithmetic sequence. And here are two geometric sequences. And again, pause if you need to, but looking at these two examples of geometric sequences, you should get a sense for what we mean by geometric sequence. If you haven't figured it out, in an arithmetic sequence, the difference between any two consecutive terms is the same. For example, 4 minus 3 is 1, 2 minus 1 is 1, 3 minus 2 is 1, and that is true about any two consecutive terms. The next term minus the previous term is referred to as D, or the common difference. In a lot of books, it's called the common difference, and we use the letter D to represent it. And again, D is what separates consecutive terms in an arithmetic sequence. So in the second arithmetic sequence, D is clearly 4. Yeah? Okay, cool. And in a geometric sequence, the common ratio, which is the ratio of the next term over the previous term, is referred to as R, and that common ratio is the same between any two consecutive terms. For example, in this first geometric sequence, 54 divided by 18 is the same as 18 divided by 6, which is the same as 6 divided by 2, which is 3, right? So the common ratio stays the same in geometric sequences, and the common difference stays the same in arithmetic sequences. And as you can see in the geometric sequences second example, the common ratio is allowed to be a negative number. And similarly, the common difference, D, can be a negative number. In other words, our arithmetic sequence might be decreasing instead of increasing. Both examples I've provided you for arithmetic sequences are increasing, but they could be decreasing. All right, cool. So with this handy then, let's try and figure out if we can come up with a formula for finding the nth term of an arithmetic or a geometric sequence. And we're going to do it in order by starting with a formula for the nth term in an arithmetic sequence first, and then we'll do it for geometric. And by nth term, I mean this. So like here, if we look at the second arithmetic sequence, 7 is the second term. So we would say that 7 is A2, where A1 is 3. And so then 15 is A4. But what if I wanted to find A17, which is the 17th term in this sequence that starts with 3, 7, 11, 15, and so on? What if I wanted to know the 17th one without like adding 3 each time? Is there a formula for that? And that's what we're about to do. And then once we're done doing that for arithmetic sequences, like I said, we'll do it for geometric sequences. So to accomplish that, in an arithmetic sequence, let's say that our first term is A. That is, A1 is A, and then A2 will surely have to be A plus D, because A2 is A1 plus D, the common difference. And A1 is A, so A2 is A plus D. And then A3 will have to be A2 plus D, but A2 is A plus D, so A3 will have to be A plus D, which is A plus 2D. And then A4 will have to be A plus 3D, and so on. You get it. All right. From this, then, let's first make the pattern abundantly clear. Sorry. Yeah, and that's to say that, like, let's write A1 as being A plus 0D, and then make it explicitly clear that D is involved in all of the terms in a way, right? Like A1 is just 0D added to like A, R star, right? Okay. And then A2 is A plus 1D. In other words, A plus D is technically A plus 1D. And then A3 is A plus 2D and so on. That way, the nth term, AN, will be easily gathered, which is that looking at the pattern of the terms that we just displayed in the previous step, it's pretty clear that A sub n will have to be A, the first term, plus n minus 1 times D. Because for A2 we had 1D, and then for A3 we had 2D. So the correspondence is for n, we need to have n minus 1D. Yeah? All right. Cool. So that's it for arithmetic sequences. This is the formula. So from here on out, I'm going to refer to this as the formula for the nth term in an arithmetic sequence. And so, like we said, we could just observe here in this second arithmetic sequence and tell that A4 is 15. Yeah? So again, if we just call back the second arithmetic sequence, it's pretty clear that A4 is 15, just looking. But what if we use the formula we just discovered? Well, using the formula we just discovered, we'd have to say that A4, since n is 4, will have to be 3, which is A1, or A, right, plus n minus 1. So when n is 4, n minus 1 is 3, and then times D, and D is 4 in this arithmetic sequence. So there it is, 3 plus 12. That makes 15, so the formula works, at least in this example, and it works every time, just not just this example. All right. Okay, and now let's do the same thing for geometric, right? Okay, that's what we said we'd do. Follow the plan. And so for geometric sequences, again, let the first term be called A, that is A1 is A, and this time we have the common ratio, which, you know, is easier to think about instead of in terms of division, in terms of multiplication. Because when I talked about the common ratio, I said you find it by doing 54 divided by 18, or 18 divided by 6, or 6 divided by 2, and it's 3. But if you think of it as multiplication, it's just the number you multiply by each time. But it's useful to think of it as both multiplication and division or ratio. Yeah? Okay, cool. Anyway, if we think of it as multiplication, we know that the common ratio is r, and that's the number we multiply by. So in a geometric sequence, if the first number A1 is A, then A2 must be A1 times r, that is A times r. And then A3 is A2 times r, and A2 is AR, so AR times r will be AR squared, and A4 is AR cubed, and so on. Easy enough to gather that. And so again, if we make it very clear, if we make it very clear what's going on, then we could say that A1 is equal to A times r to the 0 power, where r to the 0 power is 1, right? And so on. And so then it's pretty clear to gather that AN is equal to A times r to the power n minus 1. So if we revisit this first geometric series, or sequence, my bad y'all, sequence, this geometric sequence 2, 6, 18, 54, then it's pretty clear that A4, the fourth term, is 54. And let's check that that's the case using the formula. And so using the formula, we'd say A4, where n is 4, would have to be A, the first term, which is 2, right? And then times the common ratio is 3 to the power n minus 1, and n is 4, so to the power 3 to the power 4 minus 1, and that gets us 2 times 3 cubed, that's 2 times 27, which is in fact 54. So good, the formula works. All right, now if you have a sequence, I said a sequence is a list of numbers that generally has a pattern to it. So the pattern doesn't have to be arithmetic or geometric. The pattern can be defined recursively, or otherwise. So let's look at, like, before we conclude, one other type of a sequence. That way we know that all sequences are not just arithmetic and geometric. So some sequences are neither arithmetic nor geometric. a very famous sequence that is neither arithmetic nor geometric is the Fibonacci sequence. And I actually have a video for third grade students on the Fibonacci sequence, but here it is. And the Fibonacci sequence is defined recursively. And what that means is that the nth term is defined in terms of like the previous terms. So in the Fibonacci sequence, the nth term is equal to the n minus first term plus the n minus second term. In other words, the nth term is equal to the sum of the previous two terms. So, for example, the third term, f3, is equal to the second term plus the first term. So when n is equal to 3, this would say n minus 1 or 2, so f2 plus f1. So f3 is equal to f2 plus f1, and that's the case here. This 2 here is the third term, and it's equal to the second term plus the first term. And that's true of any of the nth terms in the Fibonacci sequence. They're equal to the sum of the previous two terms. Yeah? Okay, cool. And so what I just said could be summarized in writing here. And yeah, okay. And otherwise, it's typical to give the first couple of terms or just the first term when you're defining a sequence recursively. And that's my last note here. I hope you enjoyed this video. We're going to talk about series after we finish sequences. And I think you're going to find this video series, no pun intended, very good and enjoyable. In particular, when we get to infinite geometric series, we're going to be able to do a lot of interesting, cool, fun problems. So I'm looking forward to that, and I hope you are also. Keep watching. Take care.